Okay, let me get a full screen here. So this is the more traditional Algebra 2 part of the worksheet. Um, it's a tough day here today. I'm missing Renee the Cart. I did a video upstairs on the second floor, and now I can't find Renee. So I'm going to put a missing bulletin out there on carts. I don't know. I'll have to find the web page for carts and have everybody look for Renee. I don't know if somebody asked him a question and he said, I think not, and maybe he disappeared. I don't know. But we'll look for Renee later. Right now, we're going to do the Algebra 2 problems fairly quickly, just as a practice session. And I'm going to do problem 54 to 106 on the worksheet, but I'm going to start with 103 to 106. I just feel like highlighting that more, that if you are watching it, you get some good practice on name that tune. These are all tunes to me. So, it's an art class. So we're just looking at this and I hope you recognize it as a square root function. Smallest square root you have is 0, and I want that to happen at 2. So x minus 2. I want a 3. How do I get from 2 to 8 square root? When I drop a square root, when I put an 8 in here, I get the square root of 6. I get the square root of 6. I don't want the square root of 6 plus 3 because it doesn't take me to 12. 9 plus 3 takes me to 12. And that's the thought process, working with zeros and ones. I made a 0. Square root of 0 is 0. 0 times anything's easy. And then when I dropped an 8 in, I made the number 1. 1 jump of 9 takes me to 12. 10. All my y values are based on the number 10. So my first differential is 7. My next differential is 14. I think I have a doubling function, but I certainly could show 17 by adding 7. And the next time I don't want to add 7, I want to add 14. And then I make a 0 out of 1900. X minus 1900. Anything to the 0 is 1. 7 plus 10, whoopee. 1900 to 2025 is 125 years. So when I drop in 2025, I get 14 over 7 to the 1, which is 2 times 7, 14 on top of 10. Boom. Let's see if Renee, I wish I had Renee because now I'm balancing on a desk and I don't want to lose my computer. All right, so I'm measuring from 3. So x minus 3 is going to be in this equation, but we usually start with y. So why don't I start with 7? I haven't made any mistakes yet. Of course, I'm only going to get 7 if a lot of stuff disappears. 7 to 12, I'm sorry, is 5. I can see my first y and my second y. And I hope you recognize as the inverse of exponentiating is logging. And I want to measure from 3. And I know if I put an x on the board, that means I'm going to work with some numbers. So why don't I work with the number 5? Well, 5 minus 3 is 2 units of horizontal change. 2 units. What if I turn those 2 units into 1 unit? Then I've got log 1. And I don't care what the base is. That's 0. Well, I do care. I want the base to be positive because by definition, the bases have to be positive. So I got a positive base. Anything to the 0 is 1. 0 times 5 is 0 plus 7. Yep, gets me that. And then I'm going to use my second x. 9 minus 3 is 6 divided by 2. Oh, from 3 to 9 is 6 units. Oh, yeah, and that's tripling this. That's tripling this. That's 6 over 2. So I now know my base is 3. So let's put 9 in here, which gives me log of 3. That's a base of 3. We've done enough logarithms. Everybody in the room knows that's 1. 1 times 5 is 5 plus 7 is 12. And we always want to try to deepen our understanding. So can you give me this coordinate? If you pause the video, can you give me that coordinate right now? And I guess I wish I had written this a little further to the right. Okay, well, I think it's got to be 2/3. That differential, right? Because it looks like I'm multiplying by 3 to get there, and I tried to evenly space this. I think I'm going to go down 5 and get a 2. And if I add 2/3 to 3, I think I'm at 11/3. Let's see if that works, because I got to try it. 11/3 minus 9/3 is 2/3. And 2/3 divided by 2. 2/3 divided by 2 is the same as multiplying by a half. And that changes, and I get 1/3 in here. Oh, and if I change this to a 3, if I'm not mistaken, that's the number -1. I do believe I'm going down 5 from 7. Maybe that gives you a little better feel for the trajectory of a logarithm. Takes time to learn logs. We'll keep at it for another month, maybe 3 weeks. I don't know what we have left. We're diving into trig. So what do I see? I see that maybe this is a planet where the temperatures fluctuate between 100 and 70, which means the average is 85. And I'm going to start with the average because I think we're going up and down from the average 15. Yeah, and now I'm going to do this as a sine function, and then I'll do it as a cosine function. So now I have to change these years into angles. The sine function is a max at that location on the unit circle. And if we measure from 0, I think that's 1.57 units of circumference change. And if I look at that from the radian standpoint, I think I'm at pi/2. So I want 1900 or 2025 to act like pi/2. So I'm going to do x minus 20. That's not enough room. I'm going to have to write small and hope you can see it. I'm going to write x minus 2025 plus pi/2 and put a bracket over here. Okay, there you go. It's in the wall. Then I'm going to count the revolutions. Oh, that's one revolution right there before I start to repeat. One revolution on a circle, considering the circle is 2 pi r and we're doing a unit circle, is 2 pi units, brings me back to the coterminal position. So that's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 3.5 revolutions later, which took 26 years, is that function. Now, if I did it as a cosine function, well, the cosine function is a max. It measures the bases of the triangles we're going to be drawing. That happens at 0. So I could have written 85 plus 15 cosine 7 pi over 26 x minus 2025. And I could have put a plus 0 there. Obviously, I don't need to write that. But that is the same graph. The sine and the cosine function differ by 90 degrees. Keep an eye out for that. All right, so now we're going to do a little bit of imaginary skill work. And if you want to do these quickly in your head, all you have to do is that one. All right, that's minus 21i squared. I think this is exactly the same problem that we had on the earlier problems on this lesson set the day before or something. I recognize that number as positive 21. Right, I squared is -1, so it simply changes the sign of that coefficient. So I've got 21 plus 10. I think I can go right to writing 31 now. And then I can look at -6 plus 35, 35 minus 6, 29i. And it doesn't hurt to do the same problems over and over again. It actually connects those synapses pretty well. So I need to know what this number is. And I know it's -4√3 just by looking at it. I'm in quadrant 3, my x's and my y's. Right? We're in a coordinate system here. X's and y's are both negative. And so I got a feeling that my sign, the sign of angle A, of course, it would have been nice if I had put that there. Man, I'm a little discombobulated with losing Renee. All right, so we were looking for the sign of A. I think it's -√3/2. I think I recognize the 60-degree triangle as 1/2 √3/2 and 1. And if I multiply this by 8, then this becomes 8 as a hypotenuse. If I multiply this by 8, well, there's my 4√3. There's my 4√3. And if I multiply that by 8, there's my 4. The size of the triangle doesn't seem to matter. The ratios in the right triangle stay the same. And that's why we have an infinite number of table values coming out of a calculator to help us when we don't have user-friendly Pythagorean relationships. So that's an SAT question, being able to see that. All right, so how do I get from hypotenuse to the smallest side? I think we've got a factor of 2. And how do I get from the middle length to 8? I think it's a factor of √3. √3 is 1.73. This is multiplying, dividing this by 1.73. It's going to make it smaller. This is dividing by 2, makes it smaller. And hopefully if you see this divided by that, you're seeing that ratio. It might take 4 or 5 days of practice. We're just starting to really get into doing unit circle work. That's the gravy train. All right, so that takes care of that. Okay, so we want to know that that means cube root. Now I know what the cube root of 125 is. It's 5. And I know what 5 to the negative 2 is. And I think you do too. I hope everybody's writing that. I'm assuming most people will. What's the shortcut to this? Finding out if it's a plus or a minus 4i, right? Is it going to be a positive 4 with a remainder of I, or is it going to be negative? Well, you got to divide 35 by 2. 35 divided by 2 gives us a remainder of I. And I think, if I'm not mistaken, that goes 17 times. So I know that that's going to be minus 4i as an answer. Let's take a little more time with it now. So 4i to the 35, for those of you who have learned the pattern of 4, that's fine, but good luck remembering it 10 years from now. I think you're going to remember I squared negative 1, though. I got a feeling you might remember that. And you might remember your rules of exponents. I'm building up the 4i to the 35 here. And I'm seeing an odd number of negative 1s times negative 1s times negative 1. All right, and you do the odd ones. Well, there's one multiplication gives me negative 1. 2 doesn't. 3 multiplications gets me a negative 1. 4 doesn't. All right, and I've run out of room, but I hope you can see that when that exponent's odd, this becomes the number negative 1. Negative 1 times 4i minus 4i. And the more times we talk about it, the more touches you get on the ball, the better your skill level. But it doesn't happen overnight. So we do this again and again and again. And I'm trying to learn Spanish, so I think that's otra vez. I probably butchered that pronunciation, but I'm Irish, so I'm trying. All right. So that's done. That's done. All right, now we're here. Okay, this is asking me for exponential activity on top of m. I'm looking for the numerical activity on top of the base m. Why don't I write that a little more clearly in a simplified way? I think I know minus 3 and 7 is 4. And I think if I put that to the minus 5 and embrace the brackets here, I'm seeing minus 20. And we're starting to talk about this in terms of inverse operations. Okay, and we used e to the x to show that. We know that e to the 0.7 is approximately 2. E to the 0.7 exactly 2 when I write it that way. Okay. Now, what if I take the ln of this? That means I'm taking the ln of this, and we don't have to write base e, but it's asking the question, e to the what equals e to the 0.7. And we've been starting to look at this from the context of those are inverse operations. So my answer is 0.7 in this case. All right, let's take our time with it. All right, so I'm trying to do this. And ln of 2 is 0.7. And e to the 0.7 is 2. And this is asking the question, what do I put on top of e to get 2? 0.7. Because 2 is e to the 0.7. Inverse operations. Now we're trying to see the inverse operations for a different letter. All right, so we started the conversation in that direction, and we'll continue to have it until the synapses in your brain those little light bulbs that go off. We want them to go off faster. Boop, 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 boop. We want them to really go off fast. Good. All right, so we're just hoping at this stage that you know the fundamental theorem of algebra states whatever the number of the exponent is, that's how many answers you have. This equation demands 2 answers. So I hope you're writing that. Okay. The square root of -5 could also be written as the square root of 5 times the square root of -1, which I believe is the square root of 5i. -1. This is a square root. Square root of -1 times the square root of -1, it's going to get us -1. And mathematicians have decided to use the letter I to describe that amount. Conjugate. All right, so 4 plus 2 is going to get me 16 and 4 is 20. All you got to do is square the numbers. That's a shortcut, but let's take no shortcuts. And watch 20 appear. I'm going to multiply by the conjugate. Big time SAT question I hear. Okay, so can we do that in our head? That's positive 10i squared, which makes it -10 and 12. 12 minus 10 is 2. And I have -20, -6, -26i. I know I'm going to get 20 here, but let's see why. 4 times 4 is 16. The middle terms cancel. 8i minus 8i cancels. And I get -4i squared. What did we say I squared does to -4? It makes it +4. There's your 20. 2 minus 26i. Boom. And of course, you could reduce that, right? You could divide 2 out of everything. You get 1 minus 13i over 10. And you probably should do that at this stage. All right, so now I'm going to solve this using inverse operations. I'll make some room here. And this is what I'm hoping your brain is starting to do with those little light bulbs going off. I'm hoping you add 6. I'm hoping you divide by 5. I'm hoping you do the inverse of e to the, which is the ln of 4. And then I hope you multiply it by 3. And that's your answer. So let's put our answer here. 3 ln of 4. What happens to the 3's? They cancel. What is e to the ln of 4? It is 4. Times 5 is 20. Minus 6 is 14. You're pausing the video each time, right? I mean, I can't say that enough, and I don't say it enough. But before I do this problem, I'll read it off and then pause the video and write the answer. So we have an exponential function, and we want to write the function that takes 50 pounds of U232. I don't know if that's a real radioactive element or not. I just put some numbers in maybe. Every 50,000 years. So that's going to, there's a half-life here, all right? That's decaying. The radiation is shooting out all over the place, disappearing. Decaying every 50,000 years. We have half of what we started with, and we're starting that situation in the year 2024. So you pause the video, and I hope you write this. Because that describes that. All right, Renee, I miss you. I got to pick up the computer, got to move it over here. That means I run the risk of not centering the camera properly. It looks like it's better video quality today. I don't know what happened yesterday. All right, so at an algebra 2, we usually start with a sign chart. When am I greater than or equal to 0? Well, I need to know when I'm 0. That appears to be -1, and it appears to be 3. So when am I greater than or equal to 0? I know this is true. I know that's true. I know this is not true. Dividing by 0, I can't do. So that's false. I should have looked. -1, that's true. This is going to be false. This is going to be true. Obviously know something about sign changes. Let's put 4 in. 4 minus 3 is 1. That's 10. Is that number greater than or equal to 0? That's why I said true. Let's put 3 in. 3 minus 3 is 0. I can't divide by 0. That's why that's false. How do I know this is going to be false? because one of those is going to change. When I put 2 in, put 2 in, that's still positive. It used to be positive, and I divided by a positive. It's still positive when I put 2 in, but what happens here? 2 minus 3, negative. Oh, that's false. And I know it's going to change again here for the same reason. So this answer is negative infinity to -1, and -1 works. Union 3 does not work, but everything after it does. Now, I also could have graphed this. As we're learning rational functions, how to graph them. I know that this end behavior goes to 2. Y equals 2 on both sides. We'll talk about that more as we go along. I know my y-intercept is -2/3. I know my x-intercept's -1. So there we have that. Over here, we have an asymptote at 3. So x equals 3 is here, and no more x-intercepts. There's only one time this equals 0, and that's when the numerator is 0. So it has to look like that. And it looks like if this is 3, all of those y values are bigger than 0. Yes, all those y values. Oh yeah, that's why I wrote that. And it looks like over here at -1, all of these y values aren't. So what intervals work? You're looking at them. All right, so now we're solving this, which means I can erase this. Oh, what's the x-intercept? There it is, -1. So I'm glad we graphed it. It's when this equals 0. Division by x minus 3 becomes multiplication by x minus 3 on that side to help you see that the numerator equals 0. That's how you find your roots of those rationals. Set the numerator equal to 0. And that only happens one time. All right, now I'm going to do that really quick. Light bulbs in the brain by doing what? Multiplication becomes division. 1/3 log base 1/3 of becomes 1/3 to the. That's the inverse operation. Let's do it real quick with log base 5 of 25 equals 2. Solving this means that 25 came from 5 to the 2. Log base 5 of becomes 5 to the. Okay, those are inverse operations. So I've done it here. We hopefully know that that is 9. Flip it and square it. And then add 6, you get 15. So you should be able to put 15 in and see how it works. 15 minus 6 is 9. What's the exponent you put on top of 1/3 to get 9? -2. And what is 5 times -2? -10. And hopefully the numbers speak for themselves. All right, here's your SAT question. You got a 30, 60, 90 triangle. And the hypotenuse is 20. Well, each time we do this is another rep. 30 degrees gets us half the hypotenuse. 90-degree triangle. And 1/2 times √3 is another way to express √3 over 2. Now I'm doing what? Making the hypotenuse 20. 20 times bigger. 20 times bigger. 20 times bigger. 10√3. So those are the lengths of the other two sides. You know the drill. I shouldn't have to give any explanation as to what this is in terms of what I'm asking. Write it as a product. So if we write it as a product, it becomes what? 4m plus 3n. And what are those numbers? Right? If I put an 8 in here for a volume, I get a 2 by 2 by 2 cube. And so what is that in relationship to that? The cube root. So if I change it to 64m3, I hope you see that as 4m times 4m times 4m. And if you can do that for both terms, then the rest is a piece of cake because we don't look here anymore. We look here, we square that. We do the product, which is 12mn. We get rid of it because we need some cancellation, and we square that. And you're done. Okay, YKTD. All right, now we're moving right along. Sound like Monty Python? The cube root of 54, x 12, y 3. Well, there's another way to write cube roots, x to the 12. What is the other way of writing that as a cube root? I just talked about it a minute ago. Means the same thing. So what am I going to do numerically? I'm going to divide every exponent by 3. And if there's a remainder, I'll leave the remainder inside. So I can take care of the x, y, z very quickly. I can look at a cube root. Try not to forget to write that, or you're doing a square root. I can see 4. I can see 3. I can see 29 as 3 into 29, 7. No, for God's sakes, 3 into 29. Come on, Jimmy. 27, 9. 3 times 9 is 27, which means there's a remainder of 2. These are taken care of right there. Now, 54. You need to know the cube roots of 8, 27, 64, and 125. Those basically are the ones at the high school level. You got to memorize those. So what is 54? 54 is 2 times 27. And I know the cube root of 27 is 3. So that can come out. And there's your answer, which you could write organizationally better, I'm sure. All right, so what do I have here? I have 3 multiplications. If I'm looking at this one, I'm looking at root 6 times root 6 times root 3. That's root 18 in factored form. If I'm doing the second multiplication, not this one, but that one, then I'm writing root 6 as root 3, root 2, and I'm writing this as 5, root 3, and it's all multiplication, and I'm seeing root 3 times root 3 now. That's very helpful. And then the last one, root 6 times root 6, I hope you're saying 6 right off the bat. So what does this one become? This one becomes 6 root 3. That's our first multiplication. This one is root 3 times root 3, which is 3 times 5, 15 root 2. And then the last one is root 6 times root 6, which is 6. And I don't see any like terms. This is kind of like saying 6x plus 15y plus 6. I can't do anything with that. Therefore, I can't do anything with that. All right, I got compound interest, $20. I want it to double at 4% interest. I'm going to get the ln of 2. That's the doubling exponent. 4%, 0.04. We know this is approximately 0.7 divided by 0.04. Multiply everything by 100. You move the decimal place over 2 units, which gets us 70 divided by 4, which is equal to 15, 16, 17 and a half years. Hope I did that right. Now let's do it more slowly. A, if it doubles, let's start with $20. If I double it, it's $40. E, interest rate, 4%, 0.04 T. Okay, now if I'm going to double, I certainly want 20e to the 0.7. So I hope you can see why this has to become that number. And that number is the ln of 2 divided by 0.04. Still not taking any shortcuts though. Divide by 20, you get 2 equals e to the 0.04 t. How do we solve this? The inverse is ln. The inverse of e is ln. Equals 0.04 t, which I'm hoping you can see over here. Make that connection. And so that gives us the ln of 2 divided by 0.04, which I did a minute ago. So there's this modern technology. You can click on the video, you can put it, you can get a little touch on the ball, and maybe you speed up your calculations the next time. I can't take Renee over to the next 2 problems. So I'm going to have to move the desk and hope the computer doesn't fall. Oh boy, I miss Renee. I've got people looking for him. All right, so 3e to the ln of 8. Maybe you're seeing that as 3 times 8 now. Maybe you are. I hope so, because these are inverse operations. So that's 24. And there they are again. That's minus 18. My answer is 6. I could spend more time on these, but I don't think I will. Nope, not gonna. All right. We will in class, though. I'll find some easier situation to see. I'm going to add 8. I'm going to divide by 20. 2, 24, 10, 24, 12, 5, which is 12/5. If I reduce that, when I divide that, 1/2 to the becomes log base 1/2 of. These are not user-friendly numbers, so we're not going to try to figure out, 12/5 is close to 2. So this is close to -1, a little bit bigger magnitude than -1. I'm going to multiply that by 6. And then I'm going to add 5. And there's your answer. And that's how I want your brain to work. Notice we're not taking notes. No, you're going to see it again tomorrow, and I'm going to try to get you to recall. All right? Recall. It's all about you remembering. So we're practicing remembering, because when you get to calculus, you got to work with things coming at you left and right. And guess what this workshop is all about? Getting things coming at you left and right. Speaking of left and right, I'm moving to my left, and I'm doing piecewise. So let me move the desk. So what do I see? I see x minus 8. That's a linear function. X-intercept at 8. What happens when I slap an absolute value? All the negative y's become positive, and I get that reflected up. So I have a V shape, and the left side has negative slope, and the right side has positive slope, and it seems like it hinges at x equals 8. So this one becomes Alfred Hitchcock. And I know I'm going down at 2 to 1, x minus 8 plus 1, and that hinges at x equals 8. Then I'm going up at 2 to 1, plus 1, comma, x equals 8. X is greater than or equal to 8. There we go. Said it properly. And this one is x is less than 8. So yes, towards the end of the video, be careful. Carelessness is about to ensue. All right, so when does this equal 25? I'm going to erase this now. I've got the pieces over here. All right, so I'm going to subtract 1. There's 24. I'm going to divide by 12. That's positive 12, sorry. Divide by 2, positive 12. And then one of my answers is going to be absolute value means that I could look at positive, making this 12 or negative 12. So I got a plus minus 12. That means I'm moving 12 units from 8 to the right, which is one of my answers is going to be 20. And the other is 12 units to the left of 8, which is -4. So those should be my answers, right? Because I'm going to add 8. There, you can see the 20 now, and you can see the -4. That's my last step. And so I'm on a number line at -4 and positive 20. And those are the answers that make something bigger than the height of 25. All right, so the numbers in between -4 and 20 give me y values smaller. So my answer, if I did sign chart, all right, so let's take it from not the graphical, but let's do the sign chart. So I got -4 and I got 20. And I know that's going to be true, false, true, because I know that these are to linear branches, which means I'm going to get sign changes. So trial and error, there, out of breath, trial and error. Pick a number bigger than 20. I like to pick 1,000,000. Is that going to be true or false here? Bigger than 25 or not? So I'm actually on this problem. 2,000,000 plus 1, is that bigger than 25? Yeah, I think so. All right, let's pick a 0. A 0 is between these numbers. Put a 0 in. I don't think we're going to get a true statement. Oh, this is 16 plus 1 is 17. Is 17 greater than 25? Heck no. All right, so then pick a number less than -4. You're going to find it's true. So that's -infinity to -4, union 20. Did I also say or equal to? No. So therefore, it's not a bracket to infinity. And there's that series of questions that I hope we get good at. All right, now I remember 3 weeks ago, maybe I butchered this problem. If x equals -1 is a root, then x plus 1 is a factor. And so we're trying to figure out times what gets us x cubed minus 4x squared plus x plus 6. And I'm saying you can do those in your head, but if I was doing the long division, this is why you did long division in Algebra 1. I don't know if you ever did or not. I doubt it. Doesn't seem like kids are coming into class with that knowledge. So x goes into x cubed, x squared times. Up here, I would ask, what do you multiply x by to get x cubed? I hope you would say that. The way I do long division is different than the textbooks. Like everything else, I do things differently because when I do 1,000 of them, 10,000 of them, 100,000, I often find easier ways to do things. So I think the first step of easier ways to do things is if we keep taking easier and easier steps, we get synthetic division. So x squared times x is x cubed. I like to change positive. I like to change the sign and add, and it's gone. Which means if we were doing synthetic division, we wouldn't even have to write that column. We could probably just work with the numbers. X squared times 1 is positive x squared. I don't write the plus sign because I'm going to change the sign and add, and that's minus 5x squared. And then I have to bring down the x, and x goes into minus 5x squared minus 5x times. Over here, let me move this. X cubed minus 4x squared plus x plus 6. Now I got a lot of room. All right, so right now I've got x cubed and I've got x squared, but I got to get from x squared to minus 4x squared. I think I do need minus 5x. But I can see it here. I don't need to do this. All right, on this level of difficulty. So what's 1 times minus 5x? Minus 5x. And I don't want minus 5x. I want positive x. I think I got to go up 6x. And if I put a 6 here, oh, I think I get up 6x, which gives me what I need. And 6 times 1 is positive 6. There's no remainder. If there is a remainder, then that's not what you're going to write for the root. Then negative 1 doesn't work because we get a remainder. But I'm getting 0 when I put negative 1 in. It's real quick to put negative 1 into this function. That's negative 1 plus 4 minus 1 plus 6. Negative 1 squared, positive 1, 4, negative 1. I'm in trouble. What did I do? I don't like what I've got there. Negative 1, positive 4, minus 1, minus 2, 6. I don't like what I wrote. All right. I got to check my work real quick, so I'm not going to do the video again. I might have to bail on this one. X cubed minus 5x squared plus x squared is minus 4x squared. This looks right. Oh, negative 1 though. Negative 1 is going to get me 6 units of change. I'm getting 8 over there. I've got some little hiccup here, and I don't want to have to write all these problems down again. So I will try to correct it and write in the answer key where my careless error is. I told you carelessness was going to win suit. So we're just going to move on. I'm not going to do this all over again. I just don't have time. So we're still getting practice in here. I'll do that on my own time and try to write something as to where I screwed up. All right, domain for this problem. Domain is what can I use? What x's are permissible to be used in this calculation? Because there are restrictions on division by 0, restriction on division by 0, square roots in the xy plane. Renee, I miss you. I miss Renee The Cart. In the Cartesian coordinate system, we only work with positive, negative numbers and 0. We don't work with imaginaries. That's a third axis. So what do I see? I see 10 is an important number and 6. Now, if I put a number bigger than 10 in, like 11, well, I get the square root of a negative. So I can't do that. So no, I cannot use these numbers. Can I use the number 10? Well, that gets me the square root of 0 over 4. Is a calculator going to be able to punch out a number there? Yeah. 4 times 0 is 0. And the square root of 0 is 0 times 0. It's one of those, which is 0. So yeah, so this number is okay. All right. Can I use numbers between 6 and 10? Let's put a 7 in. Square root of 3 divided by 1. It's no problem. So yes, I can use those numbers. Can I use 6? 6 minus 6 is 0. Can I divide by 0? No. Can't use that. Can I use numbers less than 6, like 5? If I put 5 in here, I get division by -1. Can you divide numbers by -1? I don't see a problem. And if you put a 5 in, you get the square root of 5. Can you divide the square root of 5 by -1? I think that's fine. I think that's fine. So what's my answer here? -infinity to 6. I can't use 6. I can use 10, so that's a bracket 10. And I can't use, I'm going from 6 to 10. And I'm so used to seeing that as being correct. So 6 to 10, and I can't use 6, but I can use 10. There we go. All right. Average rate of change. And you even see that. Average rate of change of f of x equals e to the x. All right, so let's get a quick graph of e to the x. And at -1, I get e to the -1. And I'm trying to get to 2, and I get e to the 2. And I'm trying to find the slope of that differential. I don't know if I want to use the word differential there, between the coordinates. All right, so that's y2 minus y1 over x2 minus x1. That's the average rate of change. Do I know what e squared is? No, I think it's a little bit more than 7. E to the -1, it's near a third. Okay, if I want to get a feel for this, this is near 7 minus a third all over 3. All right, and that will give me a feel for the slope connecting those two coordinates, just a feel. But what I gave you was the exact answer. All right, moving right along. You know the drill. I'm going to try to write that as a product, especially if I can move the camera so that you can see what I'm even working on. Hoping you're seeing that as difference of two cubes. So write it as a product. 8. Cube root of 8 is 2. The cube root of x to the 30th is 10. That's the first parentheses, which I'm going to need more space for. Shut the door so people don't hear me at all. The cube root of that is minus 5y squared, and then we build off of that parentheses to get this done. I need the other two dimensions, 4x to the 20. Minus 10 becomes positive 10, x10, y2. Squaring that gets me 25y to the 4th. That's always positive. That's always positive. I don't care if it's a plus or a minus here. These are going to be positive, and the one in the middle, if that's a negative, is a positive. If that's a positive, then that's a negative. Square root of 3x minus 3. When does that equal x plus 1? I looked at this graphically because I know this starts at 1, goes up 3 times faster than the normal square root, but it does that. And I know the x-intercept is -1 over here for x plus 1, goes up at 1 to 1. I don't think they're going to intersect. That was my first visualization as I wrote this problem. So let's do the numerics and see why it doesn't work. So I square the left side, I square the right side. And I'm hoping you can binomial square that at this stage. Certainly done it for months. All right, so 0 is equal to x squared minus x plus 4. I don't think this ever equals 0 in the real number plane. So I did b squared. This is one time where part of the quadratic formula is helpful because that sits in the square root. And if this is negative, I don't have any real answers. So 1 minus 4 times 1 times 4. By golly, it's negative. There's no real solution here. And I move on. I don't know if I meant to do that or not. I don't like to throw curveballs at you. I want foundational work. This is a great problem for binomial squaring, for visualizing the equation, so on and so forth. So, number 83. I'm introducing the term limit if this is the calculation we're looking at right there, right? I want to know when I put a really big number in, if there's a trend. So as x goes to big, what does 2x squared minus 4x plus 7 over, I'm going to multiply this out this time, x squared minus x plus minus 6. All right, so as x gets big, these terms drop out of the problem. I mean, take a billion, square a billion, 9 zeros, square 18 zeros. This still has 9 zeros. That means that's how much bigger that sort of is. That this term is that when I put a billion in. All right, so I hope you see that that disappears, and this goes to 2. All right, that's that answer. And what you'll find is if ax to the n, if that's the big, and bx to the n, if you have the same coefficient, same powers, then that reduces to a over b. And this was really 2 over 1 x squared, 1. 2 divided by 1. That's how I knew immediately that that was going to 2. So what does y go to? 2. Now, x goes to big is exactly what this is saying. So I rather give you the limit terminology so they get used to it, so that when you get to a calculus class, the teacher doesn't have to spend 2 or 3 weeks talking about limits, because you got a little familiarity with it before you get into that class. Because if you're spending 2 to 3 weeks on limits in a calc class, in a semester model, good luck learning the calculus. All right. Rules of logs, this isn't the friendliest one, but subtraction comes from division of quantities. So I can divide x by x minus 1, and I can move 4 to the other side to be 4 to the 1. So x is equal to 4x minus 4. So 3x equals 4. So my answer is 4/3. Unless I made a careless error. X equals 7 plus or minus 4i. Textbook would put that in factored form. I think it's much easier to see this thing. I wrote it right. We're trying to figure out what x equal, well, what gets us 0 equals ax squared plus bx plus c. That's where we're trying to get. Maybe I should put the 0 on this side, because that's where everything is right now, on the right. So I think I got to move everything to the left. X minus 7 equals plus minus 4i. I'm going to square this. X squared minus 14x plus 49 equals this thing squared, which is 16i squared. And 16i squared is negative 16. So I'm going to bring 16 over, and I'm going to get x squared minus 14x plus 65 equals 0. Now, just to prove that that's the answer, I'm going to complete the square, which is putting this in graphic form. But I'm going to do it this way. All right, 7 squared, I got rid of it. So what is that? It's x minus 7 squared plus 16 equals 0. So what's that become? X minus 7 squared equals negative 16. I hope you can see minus 7 comes to the other side, plus minus the square root of minus 16, which is plus minus 4i. All right. Oh, still over here. No, we're done with that. Let's go. I almost said let's go Renee, but I can't because Renee's lost. Oh, that's too bad. Long video here, but going to get total recall. You got to keep practicing. So just when you have an isolated x, when you can isolate x with the inverse operations, just envision how would you solve this for any number n? Well, I think you would subtract 7. I think you would divide by 5. And I think you do the inverse of ln, which is e to the. Now, how do I make this a function in terms of x? Take that number and turn it into x. How do I check if this is right? Pick a number that's easy. How about 3? ln of 3 is approximately 1.1. 5 times 1.1, 5.5 plus 7 gets me 12.5 approximately. So I put in a 3 and I got approximately, I already forgot what I said, 12.5 as an approximation. So let's put 12.5 in here. 12.5 minus 7, 5.5. 5.5, 5.5 divided by 5, 1.1. I wonder what e to the 1.1 is approximately. 3. So the output of this equation, the output is the input over here. Good to know. Let's do this quickly here. 4 is 2 to the 2. 8 is 2 to the 3. So it looks like the rules of exponents come into play because the bases are the same. 2 times 3x minus 2 is 6x minus 2 if you do the distribution properly. 3 times x plus 1 is 3x plus 3. I think we're home free. I'll bring the 3x this way. I'll bring the minus 2 that way. And it looks like 5/3 will make that equation truthful. All right, I want to get in the habit of understanding e. The function e changes all exponential functions can be written in e notation, which means that the world is working with the same base, logarithmically and exponentially. But you got to know what approximately 2 is in e notation, 0.7. And you got to know that multiplication, power to power is multiplication, so that 0.7 can go there. And I think this is elementary school math, and I think when you divide by 10, decimal places go to the left. And 1, 2, 3 places. 1, 2, 3 puts it there. And if you saw 0.7, well, then you know that you're doubling. And 10 years, 100,000 years, you can sort that out. And it would have some meaning for you. In fact, whatever you have for an exponent here, whatever that exponent, if you solve whatever's written there for 0.7, then you know how long it takes to double something. And I think bankers use that and they call it the rule of 7. I have to go talk to a banker. Probably should anyway. Got to check my portfolio. Your retirement accounts have been taking a bit of a hit. Maybe it's time to, well, I don't know. Maybe a run on the bank's coming. Hope not. Who knows? Lordy. So we have been practicing this problem at the Algebra 1 level. What does it become when we make this greater than 0? Well, we can talk about the exponents. Do we get a sign change or not? If I have 3 things and they're both positive, they're all positive, I think that's a true statement. But what happens if one of them changes, just one of them? Well, it's not true anymore. So I think I can start with the roots. I see 5, even exponent. I'm going to put a dot there. I'm not going to get a sign change. Whether I put 6 in or 4, I'm going to get the same thing, a positive, out of this factor. Whereas a 6 and a 4 here, it doesn't seem to affect that at all. A 6 or a 4 here doesn't seem to affect that at all. And I don't get a sign change. So if this is true, then that's going to be true. Now we're going to have those conversations. You're going to have to work with the numbers. Remember my rule of 4. Rule of 4. In this class, we've had a rule of 4. I haven't said it lately, but until you do something 4 days in a row for 2 minutes, 4 days in a row, I don't worry about you. Usually day 4, things happen like, oh, I start to see that. The little bulbs in the head start to go off. Right now, you're just trying to follow. So I'm going to put 1,000,000 in here. And if I put 1,000,000 in here, I see that's true. And what's my biggest? 5. Let's get all the roots. -1. I'm going to get a sign change there. No sign change at -3. So I'm going to put a dot at -3, no sign change. So I know that this is true, no change. True, change. False, no change. False. And I'm doing this very close to the board and multitasking by talking to you. So it could be carelessness. Could be carelessness. But let's graph this now, because in calculus, you're very helpful to be able to graph this. So I've got a that, a that, and a that. All right, so we have shown, I hope, that when I put 1,000,000 in, you see that it's true. Polynomials, M behavior looks like that. So it looks like this. I think that's what I'm looking at. Yeah, false, false. This is negative. This is negative. Yeah. And I wanted or equal to. No, I didn't say or equal to. So therefore, I'm looking at the interval -1 to 5 union 5 to infinity. That's where I'm true. We got to just keep working with it. And then when you learn to graph it and you look at derivatives in calculus, like you're looking at rate functions. If this is a rate function, maybe it's a second derivative, maybe it's all about acceleration. And if grandma's on Route 91, we want to know when she's accelerating, decelerating. We want to know her velocity. Graphs can give you that information quickly. It takes a little longer to do it numerically. So we want to learn how to do that. That's going to take practice. And we don't have that much time left in the semester. But we've closed a lot of gaps. Very happy about the gaps we're closing. So now let's solve this quickly. And I'm hoping that by the end of the semester, this is going to be a 7-second question. Just enough time to write the answer. So I haven't looked at it yet. Let's look at it and see how long it takes. 3, 1, ln of 1, 0, plus 2. I think my answer is x equals 2, but that was pretty quick. So let's slow it down. Subtract 1, 3, divide by 3, 1. Inverse of e is ln. And I know the ln of 1 is 0 because e to the 0 is 1. So the ln of 1 is 0. And minus 2 becomes plus 2. So let's put a 2 in there. Minus 2 is 0. Anything to the 0 is 1. There's your 4. Just in case you want to make sure on a test you're right. Long video here. But each time we do this, we can get quicker, faster, stronger. Y varies directly as x. You're going to write y equals kx. 3 gets us 6. So 6 equals k times 3. Looks like k is 2. So now I'm going to write y equals 2x. What happens when y is 10? When y is 10, it sure looks like x is 5. So over here, we started with a 3 gets us 6. Now we have a 5 gets us 10. What did 3 do to 5? It got bigger. What did 6 do to 10? It got bigger. That's called direct variation. All right, this is not the best problem to look at for grouping this, but subtraction is, so this 2 could have gone there. And so therefore that's in the numerator, 4x to the 4th. This 4 could have gone here. So that's y to the 4th. And this is the square root of z. Because that could have been z to the 1/2. And I'm hoping you remember that exponent of 1/2. All right, and subtraction of exponents comes from division. And that's, yeah.
Are you sure?
I'm not done quite yet. Yeah, I'll be done in 3 minutes. Okay, so that's the rules of exponents, logs. Again, not a friendly one to do it with. I'll find an easier one the next time. All right, but I put something in your head. All right, now we're going to graph that. I got to do this quickly because I got a colleague that's got a question, I think. So that's, I've seen 3, 4. I'll put any number in here that's user friendly. I like square root of 25. I like 2 times the square root of 25 plus 4. So I'm going to pick 28. And if I do, I get 14. Any other value that's attached to that one's got to be there in order to sketch that because it's based off of that location, the change. All right, so that's that one. Exponential. Y equals 1. I'm going to do a 3-to-1 ratio. My first number is going to be 2, so I'm going to make my next one 6. By picking the proper x values, and that's based on e to the 0 we know is 1, and e to the 1.1 is approximately 3. So those are the 2 numbers that I'm going to make the exponent. What makes a 1 here? 8. That gives me, I want a 0, excuse me, 3. That gives me e to the 0, which is 1. So that gives me 3. And guess what 2 plus 1 is? 3. Then I want 1.1, so 5.5, 8.5. You take more time with it, 8.5 gets me 1.1. 1.1 is approximately 3 times 2 is a jump of 6 on top of 1, gets me 7. Sorry for the speed here, but you can slow it down. I can see x equals 3. Negative 3 is where I'm measuring from. It's the inverse of growth. So I'm going to plug in make a 1 here. Ln of 1 is 0, which gets me 4. What makes this 1? -2. Okay, so -2 is going to get me 4. And what makes this ln of 3? I'll plug in a 0. And if I plug in a 0, I get the ln of 3, which is 1.1 times 2, 2.2 plus 4, 6.2. Okay, x minus 3 over 3x plus 6. I know that that's going to 1/3. Both sides. Then you can ask questions in class, of course. -2, asymptote at -2. Y-intercept at -1/2. 0 gets me -1/2. X-intercept at 3. 3 gets me 0. Now I've got my picture. And that's that graph. Where's this going as we go to infinity? 1/3. And that's one of those situations where where we don't care about that when we put big numbers in, and I get a 1/3. As I move to -2 from the right, I think I'm going down to -infinity. So what would be a number to plug into this function? -2 from the right, something like -1.999. Plug that into the function, which I've already erased partly. And yeah, I erased it. You'd see that we get a very small positive number here. I'm thinking that's what we get into a what? A negative. I've lost the number, so I can't do that. Last problem. Oh no, I still got more problems. So this is 5. X equals 5. Base 2 log, so very similar to the ln. ln is base 2.71. I want to get this to be a 1, so I've got a 6. And that's going to get me 2. And then I want this to be 3, so I'm going to plug in an 8. Oh no, it's a log base 2. I was doing ln. So I want this to be a 2, right? Because log base 2 of 2 is 1. That's going to get me a 5. If I pick the right number, looks like it's 7. All right, and that's that. Few more problems here, almost done. Gonna do it quickly, but you can replay, slow it down. Okay, I don't have Renee, that's too bad. So let's see if I can move this desk very quickly. All right. This is an ellipse. That's bigger under the Y, so it's going to be an ellipse like that. 2, -4. That is going to be a change of 10. Side to side is going to be a change of 6, right? Which allows you to move these and find those locations. All right, and I should do that out for you, talk about it more, but I got collegial responsibilities. All right, so let's do this one. Y equals 1. Exponential growth. I've already done one like this, I thought. A 3 gets me 9. All right, 3 minus 3 is 0. Anything to the 0 is 1. My next jump is 16 plus 1 is 17. If I pick the right number, then I'm going to pick a 4. And you plug those numbers in and see why that is a jump of 8 and then a jump of 16. Last one. This is going to go to a height of 2. This is 2 over here. X-intercept at 4, very similar to the one we just did. -3. All right, it's almost exactly the same. Maybe it is the same. Y-intercept -8/3. Bumpity, bumpity. All right, that's done. All right, I got to go see what the colleague wants. And at least you got some practice in today. Ciao. Oh, where's the... There we go. Ta-ta.